Approximately 55 times every day, or 20,000 times a year, an earthquake occurs somewhere on Earth. Of those, the vast majority go unnoticed and cause no damage whatsoever. Nonetheless, earthquakes are commonly considered among the most feared natural disasters due to their sudden, unpredictable nature and their potential to unleash incredible devastation. Learn more about earthquakes, how they're measured, and the most impacted regions of the world on this episode of Everything Everywhere Daily. This episode is sponsored by Quince. A new year is upon us, and that means new resolutions, new goals, and maybe a new wardrobe. If you're craving a winter reset, start with pieces truly made to last season after season. Quince brings together premium materials, thoughtful design, and enduring quality, so you stay warm, look sharp, and feel your best all season long. One of the sweaters I recently got from Quince is something that I have been wearing almost every single day, and I love it. By partnering directly with ethical factories and top artisans, Quince cuts out the middleman to deliver premium quality at half the cost of similar brands and often even bigger discounts. Moreover, those competitor prices are often listed right on the Quince website. Refresh your winter wardrobe with Quince. Go to quince.com/daily for free shipping on your order and 365-day returns. Now available in Canada too. That's QUINCE.com/daily. Free shipping and 365-day returns. Quince.com/daily. This episode is sponsored by Mint Mobile. Now that the holidays are over, you might be feeling like you got a big spending hangover. The drinks, the holiday food, the gifts, it all adds up. Luckily, Mint Mobile is here to help you cut back on wireless spending this January with 50% off unlimited premium wireless. You can get 3, 6, or 12 months of unlimited premium wireless for just $15 a month. All plans come with high-speed data and unlimited talk and text, delivered on the nation's largest 5G network. And that's why I recommend Mint Mobile. You can get the same mobile experience you have now, but for less money. This January, quit overspending on wireless with 50% off unlimited premium wireless. Plans start at $15 a month at mintmobile.com/EED. That's mintmobile.com/EED. Limited time offer. Upfront payment of $45 for 3 months, $90 for 6 months, or $180 for 12-month plan required. $15 a month equivalent. Taxes and fees extra. Initial plan term only. Greater than 50 gigabytes may slow when network is busy. Capable device required. Availability, speed, and coverage varies. See mintmobile.com. There have been many examples of disastrous earthquakes in history, including a few covered on this very podcast, such as the 1964 Alaska earthquake, the 1970 Ancash earthquake, and the Great Lisbon earthquake of 1755. Rather than focusing on yet another devastating earthquake, in this episode I want to focus more on what causes earthquakes, how they're caused, and how we measure them. An earthquake is simply the Earth's surface shaking from seismic waves, which can range from completely undetectable to city-destroying. The seismic waves, or vibrations that travel through the Earth, can be caused by both man-made and natural events, although they're primarily the result of geologic processes. Prior to the theory of plate tectonics, earthquakes were often attributed to mythological explanations or understood through the outdated concept of geosyncline. The concept of geosyncline held that there were unstable and stable regions of the Earth's crust. When the planet rotated, unstable areas would collapse, resulting in earthquakes. The theory of plate tectonics not only revolutionized the field of geology, but also provided us a new understanding of how earthquakes occur. Plate tectonics hold that the Earth is divided into large tectonic plates, which move slowly against, towards, and away from each other. These meeting points create boundaries or fault lines. Faults are where seismic activity mostly occurs, resulting in earthquakes. Seismic waves can be thought of as waves of acoustic energy, the type of energy that can travel through all forms of matter, causing particles to compress and expand, which, when it passes through the Earth, creates what we call seismic waves. Seismic waves from earthquakes occur below and on top of the Earth's surface. There are 4 types: primary, secondary, love, and Rayleigh. Imagine these waves as ripples in a pond. Each wave is identifiable through its unique motion. Primary waves, also referred to as P waves, are the fastest type of wave. They are one of two elastic body waves, which are vibrations that can travel on all different types of the Earth's surface, be it solid, liquid, or gas. Primary waves are compressional. They move in the same direction as the seismic activity. These waves go through periods of compression rather than being released in a single direction. Secondary or S waves are also elastic, but are more destructive. Unlike their primary counterparts, S waves can only move through solids. These waves move in a shearing motion or side to side. Think of the type of wave you get when you hold a rope on one end and move it up and down. Love waves and Rayleigh waves are surface waves. Their strength decreases rapidly with depth. Love waves, also known as Q waves, propagate perpendicular to the surface. These waves also move side to side, causing the ground to resemble a wiggling snake. These waves can be some of the most destructive to infrastructure. Rayleigh waves are the other type of surface wave and also move in a perpendicular motion, and they move similarly to a water wave, except that the wave's top tends to move backwards. Rayleigh waves move in a rolling motion and can be incredibly destructive. These are amongst the most severe types of earthquake waves. They're essentially the amplitude of the earthquake. There are 4 different types of earthquake: tectonic, volcanic, collapse, and explosion earthquakes. A tectonic earthquake occurs when there is a sudden slip or movement at one of the Earth's tectonic plate fault lines. The Earth's crust is broken up into different plates composed of 2 distinct types of crust: continental and oceanic. Plates on the Earth's crust move slowly, driven by mantle currents from below. As the plates move, they push, separate, and slide against other plates, creating fault lines. These fault lines can be categorized into 3 distinct types: convergent, divergent, and transform boundaries. A convergent boundary is a subduction zone where plates collide against each other. This phenomenon typically occurs at oceanic-continental boundaries or ocean-ocean boundaries. At ocean-continent boundaries, heavy oceanic crust subducts under the lighter continental crust. This can create massive earthquakes, volcanoes, and mountain ranges such as the Andes in South America. A divergent boundary is the opposite of a convergent boundary. Here, plates are moving apart. New crust forms between the plates to fill the gaps. This is known as seafloor spreading, and it can be seen in the mid-Atlantic rift in the middle of the Atlantic Ocean. At divergent boundaries, earthquake activity is often shallow, but volcanic activity still persists. This mostly occurs between oceanic crust, but sometimes between continental crusts. Perhaps the best example of this would be Iceland. A transform boundary is when 2 plates move horizontally against each other. This doesn't create or destroy crust, but rather forms large amounts of friction. When the pressure between 2 plates builds up too much, the fault line will slip, causing massive earthquakes. And this can occur between any forms of crust. The best known example of this would probably be the San Andreas Fault in California. The second type of earthquake is a volcanic earthquake, and these are often caused by, you guessed it, volcanic activity. A volcanic earthquake is caused by a slip or a fault line near a volcano. Volcanoes are typically located in areas where the crust is weaker, and the mass of the volcano itself adds to the pressure on the weaker crust. Therefore, earthquakes can be caused by this buildup of pressure. Additionally, when magma erupts from a volcano, the change in pressure from the magma being released or entering the volcanic system can also cause earthquakes. These earthquakes are typically small and remain unseen at the surface, resulting in weaker shaking. The third type of earthquake is known as a collapse earthquake. These are typically caused by underground structures failing, resulting in the surface dropping rapidly. This structure can be a cave or a sinkhole that collapses in on itself, releasing seismic waves as the crust drops from the surface into a cavern. These earthquakes are usually much smaller than tectonic or volcanic earthquakes, but they can cause significant damage in a very small area. And the final type of earthquake is known as an explosion earthquake. These are triggered by large explosions, which are typically man-made and are caused by mining operations or the detonation of bombs. The sudden release of energy from the explosion can create a shockwave. The shockwave emulates the waves caused by natural activity. These earthquakes can be just as powerful or damaging as many natural earthquakes, at least in a limited area. The way nations can tell if nuclear tests have taken place is primarily via seismic monitoring. Earthquakes are measured on the Richter scale. The scale was first developed in the 1930s by Charles Richter and Benno Gutenberg. The initial ideas of the Richter scale were presented in one of Richter's papers in 1935. The paper presented a magnitude scale, which was later renamed to the local magnitude scale. The scale uses an equation to calculate the amplitude of a recorded seismic wave, determines the epicenter location, and then is modified to include the affected distance. This method of earthquake recording is not commonly used by most seismological authorities today. In the 1970s, the scale was replaced by a more accurate system of measurement. The Richter scale was really only accurate for recording earthquakes within a certain distance of the seismometers, specifically in California. The readings were also inaccurate for very large earthquakes. The primary measuring system for earthquakes today is known as the moment magnitude scale. This scale is often mistakenly referred to as the Richter scale, which is why the term is still used today. The moment magnitude scale measures the different types of waves generated by an earthquake, ensuring that the data from all the waves is collected and providing seismologists with a better understanding of the potential shaking and damage caused by the waves. This allows us to better show how the tectonic plates move, the amount of fault friction and slippage, as well as the size of the fault line. The magnitude scale can be measured by seismographs by determining the amplitude of the seismic waves, the distance these waves are measured, and the depth of the earthquake. The distance and amplitude are then combined into a formula which yields the magnitude. The magnitude increases roughly 30-fold to the next level. And that means a magnitude 7 earthquake releases about 32 times more energy than a magnitude 6 earthquake, and about 1,000 times more energy than a magnitude 5. The scale of earthquakes is technically unlimited, although we've never had an earthquake exceed magnitude 9.5. With our current understanding of geology, earthquakes with a magnitude of 10 should not be possible. The most powerful earthquake in recorded history was a magnitude 9.5 quake that struck Valdivia, Chile in 1960. The way the current scale can be understood is that earthquakes that are a magnitude 0.1 to 6 are at most slightly felt and create at most small damage. Earthquakes of 6 to 7.9 are large and can cause significant damage, and those above 8 are considered great earthquakes that can destroy complete communities. There are a few regions on Earth that are more prone to earthquake activity than others. The most well-known of these regions is the Pacific Ring of Fire. The region itself is named after having 2/3 of the world's active volcanoes, but it's also prone to significant earthquake activity, with over 90% of the world's earthquakes occurring in this region. And the Ring of Fire is somewhat of a misnomer, as it's actually shaped like a horseshoe rather than a circular ring, but the name still holds. The Ring of Fire results from multiple convergent boundaries colliding, creating subduction zones that create a significant portion of the region's volcanic activity as well as earthquakes. There are transform and divergent boundaries also located within the Ring of Fire, which also contribute to earthquake activity as well. One of the most active earthquake regions on the Ring of Fire is located on a transform boundary, the previously mentioned San Andreas Fault, located on the west coast of North America. This transform boundary generates thousands of small earthquakes annually and hundreds of noticeable earthquakes. Another well-known area for earthquakes and seismic activity is the Alpide Belt. This region extends from the Atlantic Ocean to the Pacific Ocean, crossing Europe, the Middle East, and Asia. This area is best known as a convergent boundary that creates mountain ranges such as the Alps and the Himalayas. The Alpide Belt makes up roughly 5 to 6% of the world's earthquakes, meaning that it and the Ring of Fire make up for roughly 96% of all the earthquakes on the planet. The destructive potential of an earthquake is not simply a function of its magnitude. It depends on where it strikes, the level of infrastructure of the area afflicted, and a host of other factors. A powerful earthquake in the middle of nowhere might not even be noticed, whereas a less powerful earthquake in an area with poor infrastructure can be devastating. Likewise, the amount of energy released in an earthquake isn't necessarily a function of how much the Earth moves. During the 2011 Tohoku earthquake in Japan, which measured 9.0, parts of the seafloor shifted by over 50 meters, or 150 feet, and parts of Japan permanently moved about 2.4 meters to the east. More powerful earthquakes might move the Earth less just because there's more pent-up energy being released. We typically hear about earthquakes only when they cause significant damage. However, they occur every day. I have a program on my computer that shows earthquakes around the world, and they appear constantly. So while it may not seem like it, the Earth is a very active planet, and this is evident by the constant movements of the crust and their corresponding earthquakes, which take place every single day. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Austin Oetken and Cameron Kieffer. Research and writing for this episode was provided by Olivia Ash. My big thanks go to everyone who supports the show over on Patreon. Your support helps make this podcast possible. And I also want to remind everyone about the community groups on Facebook and Discord. This is where everything happens that's outside of the show. As always, if you leave a review on any major podcast app or in the above community groups, you too can have it read on the show.